There are three primary methods that thermal energy is transferred. When we observe the flames of a combustion reaction, we are actually observing all three of these forms of energy transfer: conduction, convection, and thermal radiation. I could say thermal conduction, thermal convection, and thermal radiation, since the word thermal is used to describe the aspect of temperature that exists in all three cases and is sometimes implied. In a typical combustion reaction involving Class A combustible materials, you are adding heat to carbon molecules in the presence of oxygen, which produces CO2, water, and even more heat energy than you added in the first place. The energy that is being added and generated during the reaction is going to excite the molecules in and immediately adjacent to the initial point of ignition as they absorb kinetic energy. Temperature is proportional to the average kinetic energy. So these molecules that were nearest to the initial point of the reaction are going to have high average levels of kinetic energy and corresponding increases in temperature. Moving about with their newfound levels of kinetic energy, these same molecules will impact the next most adjacent molecules, and the process of energy transfer will continue as the kinetic energy is passed onward. This process is conduction, the transfer of thermal energy to another body or within a body by direct contact. Convection is the transmission of thermal energy within a fluid or a gas, and is due to the differences in density created by warmer air being less dense than cooler air. As the molecules in the flame absorb additional kinetic energy, they will move about more than their cooler counterparts, bumping into one another and moving apart, becoming less dense. These heated molecules are less dense and are expanding as they move upward and are replaced by their heavier counterparts. When this occurs, additional oxygen is drawn in and further adds to the chemical chain reaction as they approach the source of the heat and become part of the cycle. It is this rising of less dense molecules and their replacement with cooler, more dense molecules that causes flames to rise up and flicker about as the molecules move upward. Recalling some of your high school chemistry, molecules are made up of protons, neutrons, and electrons. As molecules are exposed to thermal energy, the charged particles that are being accelerated will collide with adjacent molecules. This changes the magnitude and/or direction of travel for the molecule being struck and produces electromagnetic energy, also known as thermal radiation. The more that the particles are excited, the greater the amount of electromagnetic energy released. Light emitting from a fire in the form of visible flame is electromagnetic radiation that exists at a wavelength visible to the naked eye. This does not mean that electromagnetic energy stops when flames are no longer visible, and in fact, it can extend far beyond either end of the visible portion of the light spectrum. Thermal radiation is the transmission of heat by electromagnetic waves until heat is absorbed by another opaque surface. The three primary means of thermal energy transfer can be easily demonstrated with a simple candle flame. Hold a piece of copper wire in your bare hand and place the other end into the candle flame. With copper being a relatively good conductor, it won't be long before you start to feel the wire heating up in your hand as it conducts energy from the candle flame. This is thermal conduction. Now, place your hand at a comfortable distance above the candle flame. The heat energy that you feel on your hand is the result of the hot gases rising up from the candle flame and is an example of thermal convection. If you move your hand adjacent to the lateral side of the candle flame, it is out of the convection current rising up from the candle flame. The heat energy that you feel touching the surface of your skin in this position is due to the thermal radiation caused by the release of electromagnetic energy.